the construction of the Shenzhen-Zhongshan link demanded some of the most advanced engineering solutions ever deployed in infrastructure development. The underwater tunnel, for instance, consists of 32 massive prefabricated concrete segments, each weighing over 80,000 tons, carefully submerged and aligned on the seabed with millimeter precision. Specially designed seismic-resistant technology ensures the structure remains intact even under extreme environmental stress, including typhoons, strong tides, and potential seismic activity, all of which are ever present in the Pearl River Delta. Furthermore, the artificial islands are designed to support additional facilities such as emergency response centers, toll stations, and logistics hubs, further enhancing the strategic value of the link. Sustainability has also been a major consideration, with noise reduction materials and environmental protection measures integrated into the construction process to minimize the ecological impact on the Pearl River estuary's fragile marine ecosystem. The Shenzhen-Zhongshan link represents China's ability to push the boundaries of engineering, integrating cutting-edge technology, sustainability, and urban planning into a single megastructure. Let's break it down piece by piece. The undersea tunnel, a technological breakthrough. The undersea tunnel of the Shenzhen-Zhongshan link is a technological marvel, redefining the limits of marine engineering and tunnel construction, stretching an impressive 6.8 kilometers beneath the Pearl River estuary and buried at depths of over 40 m. This submerged passage is one of the most ambitious underwater infrastructure projects ever attempted. Designed with 8 lanes per direction, it far surpasses the capacity of the Hong Kong-Zhuhai-Macau tunnel. The sheer scale of the tunnel is matched only by the complexity of its construction. As noted earlier, the Shenzhen-Zhongshan link's undersea tunnel was built using the immerse tube method, where 32 enormous prefabricated segments, each weighing over 80,000 tons, were carefully floated, submerged, and joined on the seabed with millimeter precision. This may sound simple, but it is far from it. You see, the challenge was to ensure airtight connections between segments in a high-pressure underwater environment while maintaining the tunnel's ability to withstand extreme conditions, including seismic activity, typhoons, and strong tidal currents. Creating such airtight connections between segments in an undersea tunnel is one of the most formidable engineering challenges, particularly in a high-pressure marine environment where structural integrity is constantly tested by extreme forces. One of the biggest concerns was water infiltration, as even a minor leak could compromise the tunnel's long-term durability. Engineers tackled this by designing precision machine steel gaskets combined with high-performance elastic sealing materials, ensuring a vacuum-tight seal between segments. Each segment, measuring 55 m long, 46 m wide, and 10.6 m high, was meticulously aligned using a floating docking system with a 2 mm margin of error, significantly surpassing conventional tunnel construction standards. Another major challenge was seismic resilience. Given that the Pearl River Delta is prone to geological activity, traditional expansion joints are vulnerable in such environments. But the Shenzhen-Zhongshan link's engineers introduced high-flexibility seismic-resistant expansion joints that allow the structure to absorb and dissipate seismic energy, significantly reducing the impact on aquatic ecosystems compared to similar projects like the Hong Kong-Zhuhai-Macau Bridge. Air quality and ventilation were also key concerns, given the tunnel's 8-lane bidirectional layout and expected daily traffic exceeding 100,000 vehicles to combat air stagnation and carbon buildup. The tunnel features a multi-stage air purification and ventilation system with high-efficiency particulate air or HEPA filters and real-time carbon dioxide monitoring sensors. These filters capture over 90% of fine particulate matter, ensuring that air quality inside the tunnel remains comparable to ambient outdoor air by integrating a longitudinal air flow management system. Engineers also prevent vehicle emissions from accumulating in certain zones. Another critical safety innovation is the adaptive LED lighting system, designed to improve visibility while reducing driver fatigue. Unlike traditional tunnel lighting, which can cause abrupt brightness shifts when entering or exiting, this system gradually adjusts illumination levels based on vehicle speed, time of day, and weather conditions. Research from similar tunnel projects indicates that adaptive lighting can reduce accident rates by 30%, as it minimizes sudden changes in light exposure that often lead to temporary visual impairment. Additionally, the LEDs are energy efficient and low heat emitting, cutting power consumption by 40% compared to conventional high-pressure sodium lamps while ensuring a consistent and glare-free driving experience. This undersea tunnel goes beyond just being a transportation marvel. It reflects China's commitment to green, intelligent, and future-proof engineering. And this is just one segment of this impressive megastructure project. However, making it possible was not simple. Challenges and innovations in tunnel construction. The construction of the Shenzhen-Zhongshan undersea tunnel was a bold defiance of Western skepticism. When China first announced its plan to build an 8-lane bidirectional tunnel under the Pearl River estuary, Dutch and other Western engineers questioned its feasibility, arguing that the sheer size and weight of such a structure would make it impossible to maintain long-term stability. They pointed out that each additional lane would increase hydrostatic pressure by 27%, meaning that an 8-lane tunnel would experience exponentially greater stress than any previously built immersed tunnel. Additionally, the tunnel would sit beneath one of the busiest shipping routes in the world, with 10,000-ton cargo vessels routinely passing above. The risk of structural failure under these immense loads was a critical challenge. Such a challenge had never been tackled at this scale. At a depth of over 40 m, the tunnel is subjected to enormous hydrostatic pressure far beyond what is typically encountered in submerged tunnels. With every lane added, the pressure increases by roughly 20,000 metric tons. Meaning that traditional tunnel materials would struggle to maintain their integrity over decades of use. The challenge was not just about building a large tunnel. It was about creating a structure that could resist immense water pressure, ship-induced vibrations and shifting seabed conditions, all while ensuring long-term durability and minimal maintenance. To overcome these challenges, Chinese engineers had to reinvent tunnel construction from the ground up. Instead of relying on traditional reinforced concrete, which would have been prone to cracking under extreme pressure, these joints can handle lateral movements of up to 300 mm, reducing stress on the tunnel walls and preventing structural failure during an earthquake. This level of resilience surpasses the standard set by the Tokyo Bay Aqua Line, which also operates in a seismically active zone, but features expansion joints with a smaller tolerance. To counteract buoyancy forces, engineers implemented an anti-buoyancy foundation system using a combination of deep-sea anchor piles and ultra-dense reinforced concrete. Given that each submerged segment weighs more than 80,000 tons, keeping them stable without external displacement was critical. Compared to the Hong Kong-Zhuhai-Macau Bridge undersea tunnel, where anti-buoyancy was managed with traditional ballast systems, the Shenzhen-Zhongshan Link's approach provides 40% greater stability against shifting seabed conditions. Moreover, the estuary experiences some of China's strongest tidal currents, with speeds reaching 2.5 meters per second to protect the tunnel from erosion and shifting seabed conditions. Engineers used an advanced sediment stabilization system, integrating reinforced geotextile layers and dynamically adaptive breakwaters. This ensures that underwater currents do not gradually weaken the tunnel's foundation over time. A common issue in submerged infrastructure projects like the Öresund Bridge tunnel between Denmark and Sweden. What truly sets this tunnel apart, however, is its unprecedented technological sophistication. At its core lies a groundbreaking smart monitoring system, integrating 23,000 fiber optic sensors directly into the tunnel's concrete structure. These sensors provide real-time stress, strain, and temperature data, allowing engineers to detect microfractures, monitor load distribution, and predict structural fatigue before it becomes a safety risk. This level of continuous automated health monitoring is a first for undersea tunnel construction and enhances long-term durability by enabling preemptive maintenance before major issues arise. The precision and sensitivity of this monitoring system are unparalleled. The fiber optic sensors embedded within the tunnel boast a 40% higher sensitivity than comparable systems used in the West. This allows for more accurate and immediate data collection, effectively making the concrete think. This feat is so revolutionary that it was recognized by the prestigious journal Nature. The integration of smart sensing technology into traditional concrete structures transforms the tunnel from a static passageway into a self-diagnosing, self-reporting structure, significantly reducing maintenance costs and extending its lifespan.